So in this video, we're going to be looking at radioactive half-life. So these are the learning intentions from SACE that we're going to be learning about in this video. So basically, a sample of radioactive isotope decays, and it decays exponentially with time. So it decreases by a lot quickly, and then it reduces by less and less and less. It's actually decreasing by a set percentage each time. And basically what that is the half-life is the time required for a sample of radioactive nuclei to decay by half the original amount. So if the original amount was N0, the half-life is the time it takes for it to decay to half the original amount. So N0 divided by 2. And then for it to decay by another half, so if you have a half and you halve a half, you're going to have a quarter. That would take 2 half-lives. 3 half-lives would take 1/8. After 3 half-lives, it would have decayed from 50% or half to 25% or half, or to 1/8 or 12.5%. So half-life is just the time it takes for it to reduce by half the amount of the original sample. So like as I said, so say if we had 12 grams, after 1 half-life, you'll have 6 because it will have halved. After 2 half-lives, it will have halved again. So you have 3 grams, or a quarter of the original amount. After 3 half-lives, it would have gone from 12 to 6 to 3 to 1.5. And that would be 1/8 of the original amount. And then if we halved 1.5, we'll get 0.75. So after 4 half-lives, you have 0.75 grams, or 1/16 the original sample. So just to reiterate, 1 half-life is the time required for half of the radioactive nuclei in a sample to decay. And we can also plot that as a percentage of the nuclei remaining. So as we said, 100% of the sample. After 1 half-life, it's down to 50, 2 half-lives, 25, 12.5, etc. 50, 25, 12.5, 6.25, 3.125, etc., etc. You can be expected to given a graph, and you might be asked to find the half-life. So here we have the radioactive decay of sodium. And what is the half-life of sodium? So it doesn't say nuclei per second, but let's ignore that. Let's pretend it says nuclei per second. Let's say that there's nuclei. Let's say there's 400 grams. And after 1 half-life, it's decayed to 200 grams. So 1 half-life's about there, about 15 years. 15 hours. And then decay from 200 to 100. Yeah, so it's definitely 15 because it was hard to see, but it was about 15. So it's taken 30 years to go half to a quarter, which is 100. So the half-life is clearly 15 years. 15 years is the amount of, 15 hours is the amount of time it takes for the sample to reduce by half. 400 to 200, half. So 15 hours. So the half-life of sodium-24 would be 15 hours. Now, something you need to be aware of is that the half-life of a particular isotope of an element is independent of the physical and chemical state of the isotope. So later on, when we look at carbon dating, it doesn't matter that that carbon that is radioactive is joining with oxygen to form carbon dioxide. It's still going to have the exact same half-life, even if it's chemically bonded. So it doesn't matter if it's pure or dissolved or chemically bonded, the half-life's always going to be the same. So as I said, carbon dating, and also when used in nuclear medicine, this is important. The half-life is not going to change. Now, technically this graph was actually activity. It was the radiation per second. And that has a special name. So the activity of a radioactive sample is the number of nuclei that decay per unit time. And it's actually measured in becquerel. So it's just the decays per second. So 1 becquerel is 1 decay per second. 100 becquerels is 100 decays per second. And the activity is proportional to the number of nuclei. So the graph for activity also decays or decreases exponentially. So the graph is still going to look the same. Here is a activity graph, it's still going to be exponential because activity is decays per second. So if there's 200 decays per second, well, if you get down to 100 decays per second, that just means that the number of nuclei has halved. So the half-life for activity is the same as the half-life for number of nuclei remaining. And yeah, I've explained why. So it's obviously so because after one half-life we have half the remaining radioactive nuclei, therefore we have half the number of radioactive nuclei decaying, and therefore we have half the activity, because activity is just the number of nuclei decaying per second. It's measured in becquerel. 1 becquerel is 1 decay per second. So just a few worked examples to go through. So we have radium-226, and it has a half-life of 1,622 years. Sample contains 25 grams. How much will be left after 3,244 years? So if we look carefully, one half-life is that, and we want to know how much is left after that amount of time, which is 2 half-lives. So basically, after one half-life, so we're going to start off at 25 grams, and what's it going to have done after one half-life? It's going to have decayed by half. So after one half-life, there'll be 12.5 grams. So we can just halve it or divide it by 2. And after 2 half-lives, it'll drop down to halve again, which will be half of 12.5. Half of 12.5 is 6.25 grams. And all I'm doing is dividing by 2 or halving it. Either method works. Now, how many half-lives will it take before the activity of the sample falls below 1%? So below 1% of its initial activity. So remember, activity and number of nuclei, the half-lives are going to be the same. So you want it to drop to 1%. Well, one half-life, it's going to be down to 50%. 2 be 25. 3, 12.5. 4, 6.25. 5, 3.125, etc., etc. 6 will be half of that. Oh, might have to use a calculator. Don't want to stuff up. 3.125, and we can just keep dividing by 2 on our calculator until we get down. So it'll be 1.5, 625, and if we divide it by 2 again, we're finally. So it's going to take 7 half-lives to get below 1%. So how many years is this? So how many half-lives will it take before it falls below 1%? So 7 half-lives. And how many years is this? Well, each half-life is 1,622 years. So 7 times 1,622, a lot of years. So 7 times 1,622. 11,354 years for it to drop below 1%. One more example. We have terbium-160. So it's going to have 160, mass number of 160, which means the number of protons and neutrons. Now it decays via beta minus decay. So minus is when it shoots off an electron. And if it's going to have a negative, it means we're going to need to have had a positive for its charge to be balanced. So it's actually, we can work out that, and you can use your equation sheet, it's going to be a neutron to a proton plus an electron. And a antineutrino. You can use the equation sheet. So, and that is 1, 0. This is 1, 1, and this is 0, 0. Balanced. This is -1. -1 charge. It's balanced. So half-life is 73 days. In a given sample, there are 4 times 10 to the 18 atoms. tons and tons. Jesus, times 10 to the 18 atoms. Write an equation for this beta decay. So we've done beta minus decay. Determine the number of terbium-160 nuclei after 1 year. 365 days. Well, we need to work out how many half-lives have passed. So if we do 365 and we divide it by 73, we'll get 5 half-lives. And in each one of those half-lives, the sample is halving. So if we have 4 times 10 to the 18, and that's atoms, and we're going to divide it by 2, or halve it, and we're going to halve it, and halve it, and halve it 5 times. Rather than writing half times half times half 5 times, we could just write times half to the power of 5. But if you don't remember to do that, you can just keep halving it. Just take a little bit longer. So we'll have 4 times 10 to the power of 8. And we're going to times it by a half, about 5 times, or to the power of 5. And we'll get, what is that? 1, 2, 3, 4, 5, 6, 7. So it'll be 1.2. Oh, whoops, I didn't do 18, I only did 8. So good catch. 4 times 10 to the 18. And it'll get down to 1.25 times 10 to the power of 17 atoms.